It is my great pleasure to introduce all of you to Magdalena Klemun. She is one of my good friends. We've known each other for almost a decade now, having studied together under Fulbright scholarships in the US. I can with some confidence say that Magdalena is one of the smartest people I know. So I'm very interested to hear what she has to say today. Currently, she's an assistant professor at the Division of Public Policy at the Hong Kong University of Science and Technology. She's in the Interdisciplinary Program Office and a research associate also at the Massachusetts Institute of Technology. Her research examines the dynamics of low carbon energy innovation at the technology and system level, which kind of ties in with our complex system theme. She holds a PhD in engineering science from MIT and MS and BS degrees in electrical and environmental engineering from Vienna University of Technology and Columbia University. And prior to joining the Hong Kong University of Science and Technology, she was a postdoc at MIT at the Institute for Data Systems and Society. Today's talk, Magdalena is going to talk about the evolution of low carbon energy infrastructure and the need for soft technology. So technology typically contains both hardware and soft components, such as human-led processes and services needed to deploy hardware. However, these two kinds of physical and non-physical technology components tend to evolve along distinct paths. Soft costs often improve more slowly than hardware costs, and are location, site, or even project dependent, limiting progress for the technology as a whole. In solar energy, nuclear power, and geothermal energy, soft costs have fallen or even risen with time. And soft costs have contributed to large cost differences across locations. In this seminar, Magdalena will examine trends in hardware and soft costs, as well as their determinants for three major low carbon technologies: solar photovoltaic systems, nuclear power plants, and electric vehicle chargers. She will discuss new concepts and methods to understand how different components of technology costs are driven by both physical and non-physical innovation, and explore ways for policymakers and engineers to build on these theoretical concepts to inform clean energy cost reduction and decarbonization efforts on the ground. So I'm going to hand it over to you, Magdalena. Thank you very much for joining us today.
Thanks very much, Anton, for the kind words of introduction, and also thanks to Andrea for having me here in the seminar as a speaker today. I really appreciate it. I'm going to share my screen. Can everyone see the slides? All right. So in terms of questions, I would be happy to take clarification questions during the talk, and maybe we can reserve the more discussion-focused questions for after the talk. Is that roughly, Anton, how you've been handling it so far?
That's a great point. Yes, we encourage people to just type questions in the chat box as the conversation continues, and then usually towards the end of the talk, we'll open it up for questions.
Okay, thanks. That sounds great. So I'm going to be talking for about 40 minutes, maybe a little less, about lessons learned from modeling the cost evolution of three low carbon energy technologies: solar photovoltaic or PV systems, nuclear fission power plants, and electric vehicle or EV chargers. But before I actually go into today's talk, I wanted to start by discussing the few key ideas that come out of this research. Not because I want to encourage anyone to sort of take the key ideas and leave early, but because I think given the assumed diversity in today's audience, it makes sense to sort of have you go into the talk knowing what I'm inviting you to take away. And the first main idea is that how we measure technology improvement critically affects our ability to devise targeted innovation strategies. So we can be a lot more specific and targeted in how we invest research and development funds, as well as funds to scale regional and national technology markets, when we have a better sense of the sort of historically effective avenues for technology cost and performance improvement more broadly and also have a better sense of potential limits along these avenues. Now, let me just spend a minute or so on discussing what I actually mean by technology improvement and by technology. One very basic definition of technology is that it encompasses physical components, hardware, and some type of manufacturing or deployment component delivery process to enable these physical components to actually deliver a service, such as electricity. When we accept that basic definition, we can then think of technology improvement as the combination of hardware improvements and process improvements. The crucial difference between these two types of improvements is that when we change the physical aspect of a technology, when we change hardware, we typically change both hardware and deployment processes. So when you think of, in an abstract sense, a unit of a technology, when we reduce its mass by choosing a better material, we don't only change the physical properties of this technology, we may also open up new routes or methods for delivery because the component is lighter. So we're changing physical properties and we're changing process properties. In contrast, when we innovate in a component delivery process, for instance, we don't necessarily change the physicality of the technology. So when we choose a different supply chain route, we transport the exact same physical component. So this is pretty simple and straightforward to talk about and conceptualize at the engineering level, where innovations are typically implemented. It is a little more tricky to understand when we measure technology cost improvement, because then typically innovations already implemented and data on these innovations are sort of hidden in the past, and understandably what we measure are aggregated technology cost components and changes therein, such as hardware costs and soft costs. Now that's fine, but for the particular cost category that I'm going to talk about a lot today, when we associate soft cost changes primarily with process improvements, then we may undervalue the contributions from physical technology changes to changes in process costs. And so it is important to actually do the work and account for how different mechanisms influence aggregated cost components over time to draw conclusions that can then inform innovation strategies. Because, and that leads me to the second key idea, when we actually do this work, we find that changes in soft costs, which are the costs of deployment processes and services, often stem to a large degree from hardware innovations rather than process innovations, which is somewhat counterintuitive. On the other hand, process features or soft variables tend to be somewhat less influential for cost change or tend to even deteriorate and increase costs. And so given the massive need to deploy low carbon technologies around the world for decarbonization, we're likely going to need contributions from both these high-level avenues for cost improvement. So both hardware influencing hardware costs and soft costs, but also specific process innovations, which I'm referring here to as soft technology innovation. So I hope that at this point, I've been able to communicate that technology performance is determined by more than hardware. And let's make it a little bit more specific, no matter which technology. There are a few exemptions, but really most technologies, when we purchase them, we pay for both material costs, hardware costs, and soft costs. And these costs, as I've been alluding to in my brief discussion of the key ideas, are not independent. So here's a very simple example of a light bulb for my apartment I purchased when I still lived in Massachusetts. And the soft costs here, the sales tax expenses, essentially, are a simple percentage of the hardware costs. And so a hardware feature, such as the glass usage per bulb, automatically also affects soft costs. So that's an example of a soft cost hardware dependency, a very simple one. If we accept that, then we can conclude that changes in hardware and changes in soft costs are not independent. Let me give a brief example from another technology. Now we're looking across time, and here I'm showing two pictures from a car manufacturing facility in 1968 and 2019. And you can see that obviously quite a bit has changed. We can parse this a little bit more by identifying changes in hardware features or variables of this car. So the material has likely changed, obviously its shape has changed, and that's going to have influenced hardware costs over time. We also can assume that the changes in the shape and material of this car have influenced how it's welded together, which is a dependency of labor costs, which are soft costs, on a change in hardware features. We also see that hardware was added to the process, an automated welding system here. So we've added hardware costs. And before this worker here was replaced by a robot, he likely improved in terms of the task duration through experience by repeating the same task over and over again in the process that we commonly refer to as learning by doing. And so this is a contribution of a process change to a change in soft costs. Now, why am I telling you about all those interdependencies for different technologies? I'm telling you about this because multiple important low carbon technologies exhibit rising shares of soft costs. So we've seen in several of these cases, hardware costs decline and soft costs have not declined at the same rate or even increased, leading to a larger share. So even if we expect that for some of these technologies, hardware costs are going to continue to decline, at some point, if we want to drive down costs further and further, we're likely going to need to address soft costs. And therefore, understanding cost dependencies is important to support these efforts. It's also a research challenge because there is a literature gap on modeling specific technology improvement drivers. There's sort of two broad methods to address this problem. The first type of methods can be described broadly as learning curves, which understand technology unit costs as a function of either time or cumulative production. Learning curves are extremely useful to measure rates of change. They can inform cost forecasts. They're useful to compare rates of cost change across technologies, but they don't tell us very much about the specific changes in the properties of hardware or deployment processes, technologies more generally, to cost change over time. The second category of models is strongly related to the term engineering cost models. So these are essentially equations that show how different properties of technologies and their relationships affect different various components of cost. They are mechanistic in the sense that they make obvious at least some of the mechanisms contributing to different cost components, but they're inherently defined at individual points in time and at individual points in space, and as such are static and not the most useful methods to understand how different changes at the engineering and at the policy level can contribute to improving or deteriorating technology performance over time. And so a method called technology cost evolution modeling is intended to begin to fill this gap between learning curves that are dynamic but don't necessarily capture mechanisms of cost change, and engineering cost models that are mechanistic but inherently static. And at the heart of this method is actually an engineering cost model, what we call a cost equation, that shows how different features, properties of technologies and engineering relationships give rise to different components of cost. And then we use cost change equations to quantify the contribution of changes in these technology properties modeled as variables over time to the overall cost change observed in a technology between 2 points in time or across space. And finally, we use an assignment scheme to relate engineering level changes to higher order processes or emergent phenomena such as research and development and economies of scale and learning by doing, which typically drive engineering level changes in technologies. And what this method produces in a nutshell is essentially a decomposition of cost change in a technology into a ranking of the contributions of different changing properties over time or across space. And we can look at this at different levels of abstraction, sort of either at the very specific technology level or by looking at, well, or estimating how much has research and development potentially contributed, how much has economies of scale contributed. Now, the specific questions I want to address today are, first, which cost categories and technology features drive cost change in low carbon technologies? And then second, what can we learn from these analyses of historical cost trends and underlying mechanisms to inform future cost reduction or cost control strategies? And I want to start with photovoltaic rooftop systems as the first technology case. Now, to give a little bit of background, this is a technology that is sort of unique among not just energy technologies, but technologies in general, due to its rapid adoption rate since the early 2000s and also its rapid cost reduction rate. Nevertheless, photovoltaic systems currently contribute less than 5% to global electricity production based on the latest numbers, and therefore significant additional soft cost reductions are likely needed to support large-scale adoption. So here I'm showing targets set by the US government a while ago for the cost of residential rooftop photovoltaic systems. And we can see that in 2020, we were somewhat closer to the target for 2015, rather than to the actual target for that year. And soft costs, among other hardware cost categories, are a reason for that difference. So one way to potentially inform future cost reduction strategies is to examine which specific avenues of cost reduction have been effective in the past. And so when we develop a cost equation for PV rooftop systems, I'm going to refer to photovoltaics often as PV because it's shorter. This is what it looks like, and we can see some dependencies of soft costs marked in red here on hardware variables. And it is somewhat easier to formalize this as a network of cost components that can be either hardware or process soft costs, and technology properties or variables that can also either be hardware or soft variables, and the cost dependencies between them. And we can see, as I've sort of alluded to with my earlier abstract example of a technology and then the example of the car, there are three essential types of technology cost dependencies, which we've sort of developed using the example of PV, but it is a more general conceptual approach. Hardware costs most obviously can depend on hardware variables. Material costs depend on material usage per unit of output of a technology, such as power, for instance. Labor costs, which are soft costs, can depend on how much labor we use. That is also pretty obvious. But then somewhat less obvious labor costs also depend on how much material we need to deploy for a unit of technology output, and that is the light blue line. That will be quite important going forward for the results I'm going to present in a couple of seconds. Okay, so we have in photovoltaic systems all these dependencies. Mechanical installation costs here are an example where both soft cost hardware and soft variable dependencies are important. Mechanical installation costs scale, just to give a bit of background, with the area needed for a certain power output, which in turn is dependent on how efficient solar photovoltaic panels or modules are at converting sunlight into electricity. And so you have a labor cost, which is a process, a soft cost, that is dependent on a feature of hardware, a critical hardware feature actually for photovoltaic systems. Now, here I've removed the hardware cost dependencies, and we're only looking at the dependencies of the soft cost components. And we can see that both hardware and soft variables influence soft costs. Obviously, this is a static picture of costs. We don't see yet how influential any of these variables have been at changing these different cost components. And for that, we use the cost change equations I briefly touched upon earlier. And this is the result. So each horizontal bar here shows the contribution of a changing variable, a changing property of photovoltaic systems to the overall decline in photovoltaic system prices over the 1980 to 2017 period in the US. And there's a lot going on, but I just want to highlight a few key takeaways. By looking at the amount of blue here in the graph relative to the amount of red, you can sort of gauge that hardware has been very influential for cost change, and hardware variables cost 90% of overall cost improvement. For a technology that has many physical components, especially in the beginning was quite materials intensive, that's perhaps not surprising. What is quite counterintuitive though, is that if we zoom in on the contributions of only the soft costs to the overall soft decline in photovoltaic system costs, so this is the area now marked in yellow here, we see that also the majority of soft cost declines originated in hardware variables. So if you look at the area I marked here, 75% of that area are actually hardware variables reducing soft costs rather than process variables reducing soft costs. So yes, soft costs have declined, but in attributing this decline that we observe to different human efforts, we need to be careful that we don't superficially interpret soft cost declines as process improvements being very influential, because actually if we look at the whole system, these process improvements and their contributions to soft cost declines, which is shown in red here, are relatively small. Now we can also look at this in terms of the contributions of higher order improvement processes that are responsible for engineering level changes. These don't happen as a coincidence. They often happen as a result of R&D investments and factories becoming, or entrepreneurs investing in larger factories, which can then spread their fixed costs over a larger amount of units. And when we aggregate the results I was just showing earlier into these what we call high-level mechanisms of cost reductions, then we see that research and development and economies of scale have been very influential, followed by learning by doing. But most importantly, what's interesting here is that these improvement mechanisms, particularly R&D and economies of scale, that are often associated with physical technology components that are produced, developed and improved at the lab and produced at factories, that these supposedly physical improvement mechanisms have reduced overall costs actually as much or almost as much by changing soft costs, which is the light blue bar here, as they have by changing hardware costs, which is the dark blue bar here. Now, I've been focusing a lot on the US so far, but we actually observe similar results, meaning a similar importance of hardware improvement in other countries, in other major PV markets, such as Germany, as well as Japan. Now, one question I haven't addressed at all so far is where do the engineering level changes really originate? So I've alluded to research and development, economies of scale, learning by doing, these very sort of high level drivers, but these drivers don't actually change features of technologies unless there is a specific innovation, a specific improvement that can affect one or more variables in the cost equation. And so we've also gone further in this work and have used the cost equation we developed for photovoltaic rooftop systems sort of as an organizing framework to identify a set of specific innovations that have acted on photovoltaic rooftop system costs through all these technology cost variables here. And in the context of this work, in accordance with the literature, we define specific innovations as successful commercially adopted inventions. And we're choosing this particular unit of analysis rather than patented inventions here, because not all innovations that are adopted in the field by different actors involved in installing and inspecting and permitting photovoltaic systems actually appear in patent databases. So it would be more convenient for many reasons to start from patent databases, but here we've chosen to go with a more comprehensive unit of analysis, even if that has required some methodological innovation because we couldn't rely on patent databases. And so I'm going to go over this relatively quickly in the interest of time. I just want to give you a sense of what some of the work here looks like. This is a picture of the innovations that have influenced the cost of photovoltaic systems. All innovations except the innovations for the photovoltaic module itself. So these are system level innovations, and they're shown as rectangles here, and the variables that they've affected are shown as circles. And you can see, sort of in line with the cost reduction results I've shown previously, that many innovations have focused on improving the physical components of photovoltaic systems. So we see things like better thermal management strategies for inverters. These are the machines that convert DC electricity to AC electricity that can be used by household appliances or supplied to the distribution grid, or things like there was this, is there a question? There was a brief, maybe an error.
I think maybe there was just somebody's microphone. Please continue.
Yeah. Or other hardware innovations such as automated optical inspection procedures. But overall, lots of hardware innovations, and only recently we've seen a few examples of soft innovations. And what we mean by that is innovations that change soft variables without changing hardware. So process innovations, essentially. And a commonality among these soft innovations is that they're often about codifying knowledge that's been generated from previous photovoltaic system installations and making it available to other regions with perhaps less installation experience, or they're about digitalizing or automating otherwise purely human-led processes. So I think that's interesting because even though based on the data set that we've created, which is certainly not exhaustive, it covers innovations that are mentioned, often referred to in publicly accessible peer-reviewed literature and technical reports. So we also include grade literature. So the set may not be comprehensive, but we do get a sense that there are very few soft innovations and therefore also relatively few blueprints for changing processes of photovoltaic system deployment, as opposed to the many blueprints we have for changing hardware. Now, let me move on to the second technology case I want to discuss today, nuclear power plants, focusing on nuclear fission here. Contrary to photovoltaic systems, this is a technology where costs have rapidly increased in many countries around the world. And one of the contradictions currently associated with nuclear is that while it is a key ingredient to many decarbonization scenarios, whether you look at the EU, the US, or China, The current fleet is rapidly aging, and new projects face massive cost overruns and construction delays. So currently more than 90% of the existing nuclear capacity in countries such as the US is older than 30 years. And if you look at the lower part of this plot here, you'll see that even countries with a younger nuclear fleet, such as India and Korea, have 15 to over 20% of capacity that's older than 30 years. And at the same time, there are efforts to build new plants, but particularly in the West, these tend to face construction delays as well as cost overruns. And the result is a currently insufficient rate of new nuclear construction relative to what the rate should be to meet climate change mitigation and other sustainability targets. So it's, given the record of the nuclear industry recently, somewhat less surprising that the rate is not where it should be, but it is a quite grave insight that the IEA estimated in 2020 that the rate is less than half of what it should be has been in 2019, so quite far from where it should be. Now, again, the overarching theme of this talk, so what can we learn from studying reasons for cost increases, for potentially stabilizing costs or even reducing them going forward. So here again, I'm going to look at some results, present some results from the US in the time period. This time is even a bit longer, from the 1970s to 2017. Now, it's been well known for a while that the cost of nuclear construction have rapidly increased in the US. What's not been known is that this observation holds even for standardized nuclear plant designs. So here on the right, I'm showing a decomposition of the overall cost trajectory on the left into 4 standard reactor designs constructed in the US. And as you can see, for all of these, actually 3 out of these 4 designs, the first plant was the cheapest, which goes against the common engineering expectation referred to as nth of a kind, or NOAC cost reductions. And what that means is that after a certain capacity threshold, marked here with a dashed line, we typically, because of the experience that builds up, expect cost reductions rather than increases. And that's really not been the case for nuclear construction in the US. Now, that gives us a first sense that maybe standardization did not work out quite as it was planned, but it doesn't yet tell us much about different cost categories and changing technology properties and their contribution to this massive cost increase. To address this question, we've looked at data for the total at the plant level for the complete nuclear power plant over the period 1976 to 1987. We only cover these 11 years because data for entire nuclear plants broken down into individual cost categories is very hard to come by. And so at least we use this time period to sort of inform the rest of our analysis, which then spans a larger time period. So here I'm showing the contribution of the most important cost categories that contributed to rising construction costs in the US in the 1970s and 80s. There are 61 cost categories overall. Because nuclear power plants are large, have many components, many construction activities, and I'm showing the most important ones here. And as you can see, soft costs caused more than half of this cost increase. Hardware costs also contributed, but we see as the largest contributing cost categories activities such as home office services, which involves the engineering design, the component purchasing, organization of the delivery, ironically also cost estimation, as well as field job supervision. Now, to understand better which specific changes in nuclear plant technology may have contributed to these cost category changes. We've selected in this work one specific component of nuclear power plants that is somewhat representative of the civil construction cost challenges that the nuclear industry in the US has been associated with for a while. And that component is the containment building, which is a large-scale concrete and steel structure designed to shield the environment from radiation in the event of an accident, and also to shield the reactor from any external attacks. And we've developed an engineering cost model for the containment building. And again, we can formalize this and look at it as a cost dependency network. Again, we see hardware cost components, soft cost components, many hardware variables, and a few soft variables. And this is surprisingly similar at first glance to the network I was showing for photovoltaic systems. We see many dependencies of soft costs on hardware features. One example is that, of course, steel is a big contributor to overall costs, which naturally is affected by changes in steel prices over time. And when you multiply out that bracket here in the equation, I don't want to go into much more detail. Obviously, steel labor costs also depend on the total steel volume per unit of power deployed in the containment building. And so this is a soft cost hardware variable dependency. Now, how much have all these features and dependencies contributed to the overall increase in costs? This is a picture of the answer. So here again, the horizontal bars show contributions of changing containment features to the overall increase in overnight construction costs. And we split this here into different time periods. Obviously, there's a lot going on, but I'm going to break it down a little bit by looking at these time periods. So in the first time period, the same containment design was constructed over and over again. So there are no changes or contributions from hardware characteristics. Instead, we observed a significant decline in on-site productivity, which was actually much more pronounced in the nuclear industry as opposed to the US construction industry at large. And this productivity decline here shown as structural steel deployment speed, so how much material can be moved for each person hour for each worker, as well as steel deployment speed and concrete deployment speed are the most influential reasons for cost increase. Now, in the second period, a new design was adopted to essentially implement an innovation called passive cooling, where human-controlled systems used for cooling are replaced by natural air convection. And to enable that, as you can see on the right, a two-shell design was adopted to allow airflow in between the concrete layer on the outside and the steel layer or steel liner on the inside. And these two structures previously supported each other and now needed to hold up independently of each other, which required a lot more material. And so both the added hardware, the increase in material usage, as well as related to that, the added need for human labor to deploy all this additional material were the major contributors to the rising costs over the second time period. And this was exacerbated by additional declines in productivity, which are the red bars here during the second time period as well. Now, how can we make use of this information about the past to potentially inform cost reduction or stabilization strategies in the future? The method that I've been introducing and then showing some results can also be applied prospectively. So instead of populating the cost equation with historical data, it can be populated with data representing the present and then as a second set of data points representing a future point in time, which is unspecified, but we do assume that by that point in time, certain innovations have been implemented that may potentially reduce costs. And the crucial conceptual step here is to draw on the study of historical cost increasing mechanisms to design these future cost reduction scenarios. And so we essentially focus on risky variables in the sense of the variables that have caused the massive increases in construction costs in the past. Now, in the first period, I've highlighted it here once more. These were productivity variables. And so in the first innovation scenario, we assume that this issue is addressed by implementing automated construction systems to deploy both concrete and formwork. And in the second, to sort of learn from what we've seen in the second time period we studied, we assume that advanced construction materials such as ultra high performance concrete are adopted, which require less mass, less material for the same yield and tensile strength properties. So essentially, the two directions of thought here are, if now that we know that the construction process itself was where many of the problems were in terms of cost predictability, we can do two things. We can either reduce the temporal duration by using robots that do the job faster, or we can do less of the risky process by reducing its overall mass by using new materials, essentially. And so here I'm showing the contributions of these different changes to containment building cost decreases, again, assumed, estimated for the future for these two scenarios. Scenario 2, increased productivity, and scenario 3 assumes the implementation of advanced materials. Now, interestingly, we estimate that they both could reduce costs by about 1/3 from the estimated levels in 2017, which would be a not insignificant reduction, but wouldn't change the overall trend relative to the 70s. Costs would still be significantly higher than in the 70s, which sort of shows you how bad things have gotten cost-wise. In the first scenario, the single most influential variable for cost reductions is the concrete labor productivity. And interestingly, note that what was formerly a red bar measuring a feature of a human process is now a blue bar, because it's a contribution of a change in hardware, since we've introduced a robot to a soft cost. And so this is a sort of something I'm still working on in some ongoing work. There can be instances of innovation where the nature of these performance variables is also changed through the innovation itself, which is quite interesting. And then in the second scenario, we see things like the height of the foundation, as well as different building layer thicknesses contributing the most to cost reductions. And again, interestingly, as we can see by looking at the light blue bars, these changes contribute to cost reductions a lot through soft costs, again, labor costs, and not that much in comparison by changing actual physical component costs. Okay, so before I conclude, let me briefly talk about a third technology, electric vehicle chargers, a technology that sort of is undergoing and expecting massive growth in several countries. The Biden administration in April 2021 has announced a goal to deploy 500,000 electric vehicle chargers throughout the US. There are also ambitious goals in several Chinese cities and obviously in cities around the world. And so interestingly, if you look at the specific cost components contributing to these charger construction costs, we also see significant soft costs, in this case here shown in pink, from, again, concrete labor as well as cable trenching labor shown in orange. And again, we see changes in hardware being pretty influential for future cost declines. So this is again a scenario where we assume that the placement of the charger station relative to existing infrastructure is optimized, such that the quite strenuous trenching labor can be reduced, as well as electrical installation time, because we assume that a suitable circuit breaker and the new electrical panel is already present. But the biggest cost change contribution here really comes from, again, a physical change influencing labor costs. And so what I personally find interesting about this technology is that here, if we think about hardware innovation, we have to consider both the physical components of the charging station itself, but also how it relates to physical features of its environment. So is of the distribution grid, of the street environment around. So we're sort of opening up our system boundary to account for features of both the technology itself, but then also the infrastructure environment and how we can leverage that to reduce costs. So in conclusion, going beyond high-level cost categories by modeling specific mechanisms of innovation can lead to counterintuitive findings on the drivers of cost improvement. I've shown through through examples that both hardware and soft cost declines tend to originate in hardware changes. I would also caution that despite these findings, better hardware, as the nuclear example has shown, is not an insurance against cost increase, because hardware can also drive cost increase. And these past mechanisms across multiple technologies suggest sort of two broad directions for technology improvement, where the first one is the idea that we can bet on what has worked successfully in the past, which is to improve hardware, thereby improving both hardware and soft costs. So this can take a couple of different forms. In solar photovoltaics, of course, this is what's already happening. Research and development support for new high efficiency cell architectures. There are also ideas around automating certain installation processes and reducing the costs of more standardized equipment to make locational differences less important in installer experience, for example, less important for costs. In nuclear, this would take the form of megawatt rather than gigawatt scale factory fabricated plants, which is underway in different shapes and forms. And as I've alluded to just a couple of seconds ago, for electric vehicle chargers, the goal would be to optimize both station and local infrastructure design. So this is the avenue where we change the hardware, either the core technology hardware, or we're adding new hardware to the process. And then the other direction for improvement would be not to change hardware, but to focus explicitly on soft features. I don't think it's, of course, either or. We're going to need both, but one of the advantages of the second approach is that we're not going through sort of all the improvement and invention steps needed to develop new hardware again, which, as we know from many technology examples, can take a lot of time. But we're working with what we have, of course, knowing about the risks that any innovation is not embodied in a physical design, so it can't easily be shipped around the globe, and we're relying on local competence to make this work. But here we could be thinking for all technologies actually that need to be locally installed to some degree. We could be thinking about high productivity workflow design. So these are strategies to better organize installation and construction sites to make better use of human labor and essentially speed it up and improve its quality. And these designs could be derived from the use of sensing equipment for on-site monitoring of different installation activities to actually track where specifically in the installation and the construction process these inefficiencies that slow down productivity are, which is something we have surprisingly little knowledge about currently. In terms of ongoing work building on this, I'm very interested currently in trying to measure some of the non-traditional soft costs of technologies. So what we conceptualize as a hardware cost and as a soft cost certainly depends on where we draw the boundary of our cost model. And so this is typically from the perspective of a system owner. We're talking about component cost as well as installation costs. But when we widen that system boundary a little bit to think about, well, what types of costs are actually incurred in the process of trying to improve the social acceptance of clean energy technologies. So that's a big topic in the European Union right now. Then we're talking about things like the costs of the not in my backyard phenomenon. So these are things like community benefit payments to help communities improve local attitudes towards wind farms, for example, and consulting fees often involved in court cases around NIMBYism. And so we're seeing in this sort of ongoing project quite significant differences in these NIMBYism costs across countries, which may be related to the policies and these countries use to address this issue. And then I'm also working on a conceptual framework for understanding cost dependencies, particularly soft cost dependencies in technologies more generally, sort of drawing on an even broader set of technologies, because of course, nuclear and solar and electric vehicle chargers covers some ground, but there's many ways that deployment and component delivery process costs depend on the physical design of components. And so I'm trying to map these out a bit more systematically and using a data-driven method as well. All right, so thanks for the time, and I look forward to potentially some questions or discussion points.
Thank you very much for that, Magdalena. There are some questions that have come through in the chat already, and I certainly have a few questions. Bruce, you had a question. You just want to ask it instead of me reading it?
Sure. Thanks for the talk. It was really fascinating. And what kept going through my mind was how much your work is interdisciplinary. There is a very strong sense of economics as well as technology delivery going on. And it seemed to me as well that there's a very strong question of politics and ethics involved in some of what you're talking about as well. I mean, when we talk about soft costs, for example, it very much depends on the country that you are in. I'm in the United States right now, and one thing that affects the soft costs of labor is the fact that we don't have universal health care, and therefore it's built into what is essentially the cost of labor at the business level. Well, if we had universal health care, that would change soft costs, right? So, and I can think of like 100 other sorts of things. In the chat, I use the example of Amazon, which is obviously not an energy delivery company, but it's a business, and the way it has dealt with soft costs is to work people very, very hard, and to the point of some serious problems, and that's been well documented at this point. And so I'm wondering, behind the notion of soft costs, it's in your models, it's being put as a kind of variable sort of thing on par with hard costs, in the sense that they're the same kind of thing. But I wonder if they really are the same kind of thing. I wonder if there's a lot of politics and ethics built in that the models aren't really addressing. And I wonder if that's part of what would be interesting about this being an interdisciplinary project, to bring in the economist, to bring in even the philosopher or the politics person alongside of the technology person.
Mm-hmm. Yeah, thank you. I think that's a really, really important point. I think I want to make two quick points in response. One is that I would say the philosophical underpinning, to the extent that it's there in this very sort of engineering driven work, is not that reducing soft costs is the only thing that matters. There's certainly different types of soft costs, and the overall assumption is that though in the longer run, when we reduce soft costs, we likely increase demand for the overall clean energy market, which then in turn would create jobs and would make the sort of short-term loss in income for a solar installer company less important. That's one thought. The other thought is that I think of this issue of, do we really want to cut soft costs indefinitely through automation, specifically in the context of replacing human labor with automation. And I think it becomes a problem specifically when we assume that developed nations such as the US would be exporting this PV installation equipment to developing nations rather than allowing these countries to participate in these higher value supply chain with these higher value jobs. So I think there's a lot of interesting, and I agree, highly interdisciplinary work to do in further characterizing different types of soft costs to better understand, well, which are the ones that we actually want to drive to zero potentially, and which are the ones that sort of in recognition of different development stages of cities and countries, we want to maybe not reduce to zero.
Thanks very much.
Great. Andrea, you had a question.
Okay, here I am. I think it's very much close to Bruce's question. So it would be, all right, I very much, and maybe I'm being sort of slightly philosophical and slightly fantastical here, but I very much like the idea of reducing as much of the costs of a technology as possible, including all the soft costs. But wouldn't that also then require a kind of a fundamental reshaping of the way that we do the world, if that makes sense? So that, I mean, I'm thinking, yeah, reduce all the soft costs. Could we not then have like a 3-day work week and a bottom minimal wage or something like that, where we could actually use the technology in a positive way to actually improve human dignity, rather than have this terrible fear of, okay, we're going to have everything automated and nobody's going to have a job. So it was just something, you know, maybe it's fantastical, but I'd like maybe a comment on that if you have any ideas.
I mean, I think a scenario where we're shifting component delivery, installation, and construction to such a large degree to automated systems that there are no humans involved in any part of this really complex and vast process is so far away that I'm not entirely sure, and this may not be the answer you were looking for. I'm not entirely sure we need to prepare for it today, because we are in a situation where a lot of key decision makers in energy systems still argue that they cannot afford support programs for photovoltaic systems, for wind turbines, because they're simply too expensive, and that's to a large extent because of these process costs. I do fully agree that it's intriguing to think about it from a philosophical perspective, where at the end of the spectrum you would have perhaps artificial intelligence designing these technologies and deploying them. I'm not sure that this is where we want to go, but I think that in between now, where we're so far from that, in that scenario, there's a lot to learn from sort of thinking through these potential degrees of automation, these shifts of different types of human labors to factories of robots, then the replacement of even designers by robotic designers or AI designers. I think that's all that could be very valuable to actually inform efforts today that are situated at a very much less sophisticated level, I would say, if we're really trying to drive down the costs of these zero emission technologies and reduce emissions as fast as we can. Okay, thanks. Thanks very much.
Thanks. I have a question for you, Magdalena. Have you looked at the data of comparable energy production technologies that are emitting? So what is happening to the cost equations for coal fire or for natural gas installations? Are they seeing like nuclear a similar increase in cost for setting up one of these, or has there been a drop? Because the way I see it is ultimately these are kind of a battle of the economics of these two different models, right? If eventually if your renewable technologies just become cheaper, it would just be the logical choice to make. Versus if we see similar efficiency gains in, say, the way the coal power stations are being produced, it might be a more attractive proposition, especially for developing countries.
It is a more attractive proposition because you're saying because the costs have also declined, but they're still more affordable.
Well, I'm just curious how the data between those technologies compare, because you've presented all the good stuff. So it's like what's happening with nuclear, what's happening with photovoltaics. I'm curious what's happening with just like coal and coal electrical production. Are we seeing similar data coming out of that? Or
yeah, I mean, there is
the trends.
One of my co-authors, James McNerney, has written a paper on the key drivers of the costs of coal-fired electricity over time, and commodity prices, so concrete prices, contribute, if I remember correctly from reading that paper, a lot. I don't see anything in these results, though, that would, in my view, support your argument that these technologies, because we're seeing efficiency gains in construction of traditional fossil-fired power plants, would be more attractive for developing countries. I think it really depends on the local price differential between fossil-generated electricity and renewable electricity.
Okay, good, thank you. Are there any other questions?
Anton, there are a couple more in the chat, I think.
Oh, we've got one from Lizelle. Lizelle, would you like to ask your question?
She had to go off to another presentation.
Sorry, I'll just read the question. The renewable, non-renewable dichotomy should be recognized, as in renewable sources of energy are also dependent on non-renewable sources. So from a carbon reduction perspective, this is misleading. All energy supply requires distribution systems, electrical wires, that consume land and resources. The term renewable energy is therefore somewhat misleading.
Mm-hmm.
I'm not sure if it sounds a bit more like a statement than a question, but
I mean, I think it sort of reflects an important discussion that's been going on in the energy systems and also industrial ecology research community for a while, which is to account indeed for these energy inputs into manufacturing technologies, particularly important for technologies that up until a few years ago were very new, such as wind and solar photovoltaics. But these many studies on the called EROI, energy return on investment, actually show that these technologies tend to produce a lot more energy over the course of their lifetimes than they consume in the manufacturing, installation, and also end-of-life management. So it is from a sustainability and very much a systems viewpoint, a smart and sound decision to invest in these technologies. And I think that would be, if sorry, I didn't catch the name of the person who asked this question.
Lizelle.
If Lizelle would be interested in this question some more, I recommend checking out these many articles on energy return on investment.
Great. I'm conscious that we're somewhat over time, but I'm going to ask you just to make one more comment, and that is really from a practical level, what should policymakers at a national level be doing to promote sort of renewable technologies, given your findings and your data?
I personally think that there's a lot of work to do in encouraging and rewarding the sharing of effective installation practices, and most importantly, the sharing of data. So anyone who's done any work of this type, where you're really trying to dig into detailed cost increasing or cost decreasing mechanisms of different technologies, knows that there is a significant dependence on location, even on individual projects, certainly on individual installer companies. And oftentimes we sort of design methods around that and create design research that can lead to results that are robust to these uncertainties, because we don't have enough data. And that's fine, again, because we design the research such that we can actually draw conclusions, but we could draw so many more conclusions on soft innovations in individual locations for individual companies, on instances where process features have perhaps been much more impactful than what I've been showing for the US market, the German market, the Japanese market on an aggregate level, and try and export these potentially much more successful cases to other places. And what I'm thinking about there is essentially software, online portals supported by national or regional governments that allow data suppliers to gather points or other rewarding categories for sharing both very specific cost and technology feature data, and potentially sharing lessons on what has worked and what hasn't worked in practice. I think it's a very sort of fine line between recognizing the societal benefit of doing that and also damaging each individual company's ability to sell sort of what it's good at and not tell everyone about it. But I also think that the need to reduce these costs quickly, at least certain types of soft costs, and further accelerate deployment and integration of renewables is big enough, the societal need, that together with some mechanisms for rewarding data and experience sharing, this could actually work and could inform policies to then support what has succeeded, as well as further research to leverage this data. I think this could be really impactful.
Brilliant. Thank you so much. This has been hugely interesting and something a bit out of line from what we usually discuss on these talks, but I think it's been a nice gear shift. Thank you very much, Magdalena. Andrea, do you have any final words?
Thank you very much for inviting me. I really appreciated the discussion. Also for me, it's been quite different from the types of questions I usually get.
No, Magdalena, thank you very much. One of the things I just want to quickly connect very quickly is back to what Anton was talking about, maybe is the idea that one, in this kind of environment, this seems to be a very deep need for a global kind of organization of certain things. I mean, what you were talking about just earlier about sharing technology made me think a lot about the vaccine disaster in a way, and the necessity in a way to think on a world scale, a universal kind of, not universal, world scale, global scale. So, I mean, I think that what you're talking about connects very much to what Anton was talking about last week. So I'm very happy to have had a very different kind of talk. I mean, lots of it is quite sort of foreign to philosophy people, but it was very interesting. It was fabulous. And yeah, thank you very much for talking to us. And if anyone needs to look at it again, of course, we will put it on YouTube. But yeah, so thank you.
Sounds great. Thank you very much. It's been very, very rewarding to be here.
All right.
Have a lovely Friday evening in Hong Kong, and
yes.
we'll say goodbye to the rest of our guests.
Same to you.
All right. Cheers. Bye everyone.